Imagine you're falling, feet first, toward the most dangerous object in the universe. You can't see it, you can't feel it yet, but something is about to happen to your body that has no name in any human language, except one borrowed from the dinner table. You are about to be turned into spaghetti. Not a metaphor, not a joke, a real, physical process, confirmed by science, witnessed by telescopes, and violent beyond anything you can imagine. This is spaghettification, and it may be the most terrifying way anything has ever died in the history of the universe. To understand spaghettification, you first need to understand what you're actually falling into. A black hole isn't a hole. It isn't empty. It's the opposite. It's an object so impossibly dense that it crushes a mass larger than the sun into a space smaller than a marble. And here's the thing about gravity. It gets stronger the closer you get. Not gradually, exponentially. Double your distance from a black hole. Gravity drops to a quarter of what it was. Cut your distance in half. Gravity quadruples. Get close enough, and the difference in gravity between your feet and your head becomes catastrophic. That difference is called a tidal force. You already know it. It's what pulls the oceans toward the moon, giving Earth its tides. The moon's gravity pulls slightly harder on the side of Earth nearest to it. The water bulges. Tides happen. Now imagine that same effect, but instead of inches of water movement, the force difference across your 6-foot body is strong enough to rip atoms apart. That's what a black hole does to you. Here is exactly what happens to a human body near a stellar mass black hole, one between 5 and 50 times the mass of our sun. You are falling feet first. You haven't crossed the event horizon yet. You are still hundreds of miles out. And yet your feet are already being pulled measurably harder than your head. The safe distance? About 440 miles from a solar mass black hole. Closer than that, and the tidal forces begin to exceed the tensile strength of human tissue. First, your legs stretch. Not painfully. Not yet. It feels like a gentle pull, like something is slowly lengthening you. Then the pull doubles, triples, your spine elongates. Your bones separate at the joints. Your blood, your organs, every cell begins to slide toward your feet, which are now accelerating into the black hole faster than your head can follow. The technical term for this is tidal disruption. The honest term is, you are being torn apart molecule by molecule and stretched into a stream of hot plasma thousands of miles long. This entire process from discomfort to complete dissolution takes seconds, not hours, not minutes, seconds. Here is something nobody tells you, and it's genuinely counterintuitive. The bigger the black hole, the gentler the spaghettification. At the center of our galaxy sits Sagittarius A, a supermassive black hole with the mass of 4.3 million suns. Its event horizon stretches about 15 million miles across. That's more than 15 times the distance from the Earth to the Moon. And if you fell into it, you might cross the event horizon without feeling a thing. No stretching, no tearing, just crossing a line. A point of no return that you'd have no physical way to detect. Why? Because the tidal force depends on how fast gravity changes with distance. For a supermassive black hole, that change is so gradual across the span of a human body that it's virtually undetectable at the event horizon. For a stellar mass black hole, one the size of a city, the event horizon is only about 2 miles across. The gravity changes violently over tiny distances. You'd be shredded long before you reached it. So the universe's most violent death is reserved not for the biggest black holes, but for the smallest ones. And get this, there are more stellar mass black holes in the Milky Way than there are stars in most galaxies. Somewhere between 10 million and a billion of them, drifting silently through space. For most of history, spaghettification was a thought experiment, a terrifying idea, a prediction. Then, in September 2019, in a spiral galaxy 215 million light-years away in the constellation Eridanus, a star wandered too close to a supermassive black hole. And we watched. Astronomers at the European Southern Observatory caught the event, named A2 2019 KIS, just as it began. For 6 months, telescopes across the world tracked the light of a dying star being stretched into oblivion. What they saw confirmed everything. About half the star's mass, a mass larger than our entire sun, was pulled into the black hole. The other half was launched outward at 6,214 miles per second. That's fast enough to cross the entire United States in less time than it takes to blink. A whole star, gone, in 6 months. And that's a star something 1,000,000 times bigger than a human body. For us, the process would be over in the blink of an eye. The word spaghettification was first used by Stephen Hawking in his book A Brief History of Time, published in 1988. He described an astronaut falling feet first into a black hole. The astronaut is stretched like spaghetti. The name stuck. But what Hawking didn't fully explore in that book, and what physicists have wrestled with ever since, is what spaghettification means for information. Here is the problem. Physics says information cannot be destroyed. Every particle, every atom that makes you up, carries information about your state, your history, your existence. Quantum mechanics demands that information be preserved. But a black hole takes everything you are, every atom of your spaghettified body, and crushes it into a singularity, point of infinite density where our laws of physics stop working entirely. Does your information survive? Does it leak out as Hawking radiation, the slow thermal glow that black holes emit as they evaporate over trillions of years? Or is it simply erased? This is the black hole information paradox, and it remains one of the deepest unsolved problems in all of physics. Nobody knows. Not yet. Spaghettification is not science fiction. It is physics. It has already happened to a real star in a real galaxy, and we watched it. Somewhere in the Milky Way, there are black holes drifting through the dark, with no light, no signal, no warning. And the universe, as far as we can tell, does not care what happens to anything that gets too close. But here's what I keep thinking about. If information is never truly destroyed, if every atom of a spaghettified star somehow survives, encoded in radiation that escapes over trillions of years, then in some strange, physics-defying sense, nothing is ever really gone. The universe stretches everything, forces everything into new shapes. Maybe that's not only true of stars,